Yeah, so good morning, everyone. And we're really happy to have with us today Mark Taylor. Mark Taylor is the man behind TopCat, my favorite VO tool. And he's from the University of Bristol. And I have been in touch with Mark Taylor since some time because I found that TopCat is an effective tool for it's a very effective tool to use archival data, because with very little preparation or very little programming skills, students can very effectively use TopCat. And that's how we're very happy to have Mark with us today to talk to us about TopCat. And we're really looking forward to hearing from him. What we're planning is let Mark speak, and we'll have the Q&A after the talk. If you can't resist it, then please write your questions on the chat window, and we'll redirect it. So when we have the Q&A, you can unmute yourself and have your own interaction, right? So let's start. And good morning, good night to Mark Taylor. And let's start. Thank you.
Okay, thank you very much, Priya. So yes, I'm going to be talking about TopCat today. Someone scribbled on my screen. Never mind, I think it's okay. So I'll start off with an introduction for 20 minutes or so, just going through some slides explaining what it is and what it's for and what it can do. And then the second part of the talk will be a demonstration where I'll go through, put TopCat through its paces and do a couple of kind of scientifically relevant things with it. And then we'll stop and see if there are questions and answers, and I'm happy to answer whatever comes up. And then the final part of it will be a hands-on session where I'll continue to answer questions if there are any, but I'll point you at a tutorial that you can work through yourselves, and if things come up, I'll answer them. Okay, so TopCat, so by the way, I know that Priya gave some kind of introduction to it last week and went through some examples as well. But I'm going to kind of do this from the ground up and go through some things in a bit more detail and go a bit deeper on some other things. So some of this will probably be familiar to you, but I want to make sure that everyone kind of understands it from the basics. So it's a tool that's designed mostly for interactive exploration. It sits on your desktop, and the idea is that you can point it at a table, which is either a table that you understand pretty well, or maybe a table that you've got from some external data archive and it's full of columns and rows that you don't know what they mean. And you can investigate it without knowing anything initially about it, and you can look at what the columns are, what the rows are, and get deeper and deeper depending on how much effort you want to put in, and hopefully wring out the last amount of kind of astronomical information that's buried in there. And so the kind of philosophy of the tool is that it does all the boring mechanical things that astronomers need to do when they're working with tabular data. So that typically means source catalogs, but it can be other tables as well, like visualization and cross-matching and understanding file formats and talking to external data archives, so that the astronomer can think about doing astronomy and doesn't have to worry about shifting numbers from one place to another. So the idea is it's supposed to be user-friendly, and it's kind of easier it's easy for me to say. Whether it actually is for you to judge, but I try and make it easy to get started. There's just one file, so if you have Java installed, it should work okay. And the idea is that to do simple things should be fairly straightforward. So you point at a table and you start up a plot, and it will give you a plot, and then if that's not the plot you want, you can fiddle around with it. So there's certainly some things which aren't so straightforward to do, but those things are at least well documented. And the idea is you can start off doing something simple. If you want to put in more effort, try harder, read some more documentation, play around some more, you can get more out of it. It should be fairly high performance. Most things work quite quickly, and it handles fairly large tables. So even on any old kind of desktop or laptop computer, a few million rows is usually okay, and a few hundreds of columns. So I've been working on it for getting on for 20 years now, and I haven't really had a grand plan of what it's going to do in 5 years' time or 1 year time. What I've done is put something out there and then get feedback from astronomers, and they say, yeah, that's nice, but it would be nice if it did this as well, or how can I do that, or this isn't working. And so everything that it does has really been driven by input from the community, which is people like you, amongst others. So I'm always really pleased to get feedback about it, because that feeds into making it a better tool in the future. So there's a list of things here that it can do. I won't go through these now because I'll talk about them on the next few slides, but it's worth saying some things about what it can't do. So it is a tool for tables. If you've got image data, pictures of the sky, TopCat is not the tool for that. There's plenty of image manipulation tools out there that are good for that, like DS9 or Aladdin. It's for tabular data. You can't script it, so it's an interactive tool. You point and click it to make it do things, but there is an associated scripting package called Stilts, which I'll talk about just briefly towards the end. You can't do infinitely large tables. So for instance, you can't load the whole Gaia source catalog into it, which is 1 billion odd rows. Well, actually you can, but it's not a very good idea. But you can work with fairly large tables. So if you're looking at a huge survey, then you do need to do some selection before you work out what data set you want to load in. It will cope with a number of file formats, including FITS and VO table and CSV, but there are certainly some file formats it won't cope with. So you may find yourself with data in some format that it doesn't like, in which case you'll need to use some other tool to convert that into a TopCat friendly format. AstroPy could sometimes be good for that. And it won't do your astronomy for you or write your papers for it. It doesn't really do anything clever at all. It doesn't, it won't tell you what's a star and what's a galaxy. It won't work out the Hubble constant. It just gives you the tools so that you can move the data around and try and understand what it's telling you yourself. So the first thing it can do is show you the data that you're looking at. So you can look at the actual rows and columns, but importantly, it can show you the metadata as well, which means information about the data that tells you what it is you're looking at. And if the table you've got is a CSV file you've just written yourself, that's not so important. But if what you're getting is the result of a query with a table with hundreds of columns on it from a survey that you haven't looked at before, then it's important to be able to understand what those numbers actually mean. And so TopCat, if the original data provider has put that information in there, will give you access to that information. A lot of what you want to do when you're trying to make sense of astronomical data comes down to working out, identifying subpopulations in data. So you've got a list of objects, a list of sources on the sky, and you want to work out which ones are stars or which ones are supernovae or which ones are foreground objects and which ones are in the background. And a lot of that comes down to identifying subsets, subselections of rows within the table. And so there's quite a bit of stuff in TopCat that enables you to make selections in various different ways and compare them with each other. So you can see here, there's one thing you can do is kind of do that graphically, draw blobs around certain selections, and then label those and use those in a different context. This is a slightly different way of doing it. This purple plot here, which still lets you define things graphically, but in this case, it will actually give you an algebraic expression based on the points that you put in, which tell you what that selection is. And if you have that, then you can also apply that to different data sets than the one you're looking at. That could be useful, or communicate it to other people. Or you can point and click on rows and select them like that, or you can write an algebraic expression. But doing this thing of identifying a subset in one data space and then seeing what it looks like in another data space using linked views is often a lot of what constitutes the understanding of the astronomical data. So another aspect of that, of linked views, is if you don't want to identify a subset in one data space, you're just interested in one particular point. It might be an outlier, or it might be your favorite astronomical object. And so if you click on a row, on a point in any of the plots, then the same row gets highlighted in all the other plots that you've got of the same data set. And similarly, if you click on a point, the row in the table that corresponds to that point will be highlighted as well. So you can see all the data across all the columns of the thing that you're interested in. You can configure it to do quite a lot of other things as well when you click on a point. I won't go into all of those, but I'll show you some examples later on. But you can do things like communicate with an external tool. This is Aladdin running in the background, and using a protocol called SAMPA VO protocol, TopCat can send a message to Aladdin saying, okay, we're interested in this particular point or this particular sky position. Can you show me what you've got on that? So for instance, you can tell Aladdin to move to the sky position corresponding to this point. Or maybe you know an archive where there's spectral data corresponding to, there's spectral data on the sky, and you can tell a spectrum analysis program to load the spectrum associated with this point. So that's another kind of configuration you can do. TopCat comes with its own expression language, which means that you can make you can do arithmetic, algebraic manipulations of the columns. So if you have a table with, for instance, 2 magnitude columns, but what you want to know is the difference between those 2 magnitudes, you're not restricted just to using the columns that you can see. You can work out expressions combining the two. So for instance, if you've got a table with a U magnitude column and a G magnitude column, and you want to plot the difference between those two, the color, then you can just type in this expression and it will give you what you want. The expression language is pretty comprehensive. It's actually based on, or it actually is Java syntax, which in turn is based on syntax of the C programming language. But you don't need to know either of those languages in order to use it. It kind of looks like you'd expect it to look like, really. It's got, arithmetic operators, plus and minus and divided by times, use column names as variables, and various other features as well. It's got conditional expressions, which can be useful. You can say if this expression is true or false, then use this expression. If it's false, use another expression. There's all kinds of standard mathematical functions, trigonometric functions too, plus a bunch of astronomically specific functions as well, which I periodically add to if people come up with something that they'd like to see in there, which isn't already. So you can do things like converting from flux to magnitudes, or propagating proper motions if you've got proper motions and elapsed times in there, and so on. If you're enthusiastic, you can even write your own functions and plug them in at runtime. So I put quite a lot of effort into making it work for large data sets and lots of different types of data sets. So it's got lots of different, it's got a lot of capabilities. It's got lots of different plot types. Sorry, the reason I'm blustering is because I can't see the title of this slide. I think it says visualization. If it's about visualization, I'll tell you what that is. So there's lots of different types of plot that it can do, and I won't go through them all, but I'll show you some examples later. And all of those plots have got lots of different options. And again, I'll show you what they are. So when you start off a plot, it will give you something. It will plot, it'll pick a couple of, if you ask to do a scatter plot, it will pick a couple of columns and plot them against each other. And it's probably not the plot that you want to see, but it gives you something to start with. And then you can change the things it's plotting. You can change the size of the markers. You can change the way the markers are colored and the way the axes are labeled and so on. And all those things are in a somewhat complicated graphical interface, simply because there's a lot of different options to put there. But you poke around on the interface and find out what's there, and the various controls will change the plot as soon as you do it. So there's sliders and selectors and so on, and every time you change one of the controls, the plot will update automatically. The point of that is that although if people want to read the manual, that's great, I don't really expect them to for that sort of thing. You can work out how to use it, hopefully, by just kind of playing around with the controls that you've got, and you can see what happens when you twiddle something, and then you twiddle something else and see what happens when you do that, and hopefully iterate to get the plot that you're actually interested to see. I did think quite hard about working with large data sets, and there's a few different aspects to that. One is if you've got millions of rows, it wants to plot it without running out of memory, and so it doesn't use more and more memory for more and more points, at least as far as it can do that. There's another issue of representing very dense plots. So if you've got millions of rows, you have to kind of think what a scatter plot of that looks like to be comprehensible, and I'll talk about that in a moment. And large data sets also means not only a lot of rows, but a lot of columns. So if you've just got two quantities that you want to plot against each other, it's pretty straightforward. You do a 2D scatter plot. But if you've got another quantity, then you might want to find ways to represent that as well. So for instance, you can change the color of the points, or change the size or shape of the points, or maybe do an actual 3D plot. And so it gives you options for visualizing in more dimensions than just two, if you want to. And it can output in various different data formats, different graphics formats. So that's just a gallery of a few of the kinds of plots you can do. I won't go through those in any more detail. Going back to what I was saying about plotting large numbers of points in a comprehensible way. So if you've got a few million points and maybe a few 100,000 pixels on the screen, obviously you can't have one, you've got more points per pixel. And if you just do it in the most straightforward way, you can end up with a plot that looks like this. So you can see roughly which parts of the flat one, I don't know if you can see my mouse pointer. You can see that the flat one is the obvious way to do it, and you can see which parts of the screen are occupied, where there is some data, but you can't really see the structure in the bulk of it. And so by default, TopCat gives you this one at the bottom right, the auto, which looks like a normal scatter plot where there's just a few points, but where there's lots of points piled up on top of each other. It darkens the colors like this so that you can see the structure of the data. There's variations on that, so you can choose different kinds of ways to represent the data. You can choose this flat one if that suits you. There's transparency, you can do contour plots. This density one is also quite useful. It's kind of like the auto plot, but with more options. So you can choose the color map, you can choose how the density maps to different places on the color map, and so on. Cross-matching is an important bit of the functionality. So that's when you've got two source catalogs and you want to work out which object in one catalog corresponds to the same object in another catalog. Presumably, you might have an optical data and some infrared data from two different telescopes, or something like that. And there's various ways that you can do it in TopCat. The most straightforward one is what I've illustrated here, this match tables window. This is what's known as an internal match. And in that case, you load, if you've got both tables that you want to match loaded in TopCat already, then you just tell it which one it is, the first table, and you say which the position columns are. And then you look at the second table, tell it which the position columns are there, and tell it how far away an object in one catalog has to be from an object in another catalog to count as a match, and then hit the button and it will go off and go through all those objects and work out which ones correspond, and give you a new table as output, which is the join of the two input tables. So that works quite well up to a million odd rows each. Doesn't take too long. And there's various options you can have. If you've got elliptical error bounds or something on it, you can use that as well as just simple distances on the sky. That doesn't always work. For instance, if you've got your own catalogue of your 100 objects that you've observed, and you want to work out which ones of those are in, for instance, the Gaia source catalogue, you can't download the whole Gaia source catalogue into TopCat, it's too big. And so there are various different options for matching with an external catalogue, which come down to one way or another. TopCat sends the information that it's got to an external service which has the large catalogue, and the external service somehow or other does the calculations and then sends the join table back to TopCat. We'll talk about a couple of these options in the demonstration. Virtual Observatory hopefully isn't an idea that's new to you, but just so we know what we're talking about. So one way that I like to think about it is if the World Wide Web is as if it's all the documents in the world sat on your computer and you can just look at them. The idea of the Virtual Observatory is that it's as if all astronomical archives in the world are sat on your computer and you can look at them. Now it's, well, like the World Wide Web, it's not always completely reliable, doesn't always work that way, but that's the intention. And again, like the World Wide Web, it's not a big data warehouse sat somewhere with a lot of disks. It's a set of protocols which allow different agents, so for instance, a software client like TopCat, to talk to external services in a standardized way. So I can write some code which says, this is how I do a cone search, or this is how I do a tap search. And then TopCat can point at lots of different services and use the same code in order to talk to those. And that means you've got access to many different archives around the world. So it makes life easier for me that there's the standardized protocols. I only have to write it once. It makes life easier for you because you only have to understand one interface. They all look the same. They've got different data in, but they behave the same way. So as a software user, you don't need to understand the details of all these protocols, the specification documents there, if you like that sort of thing, but you mostly don't need to know how it works. But it's sometimes useful to have a rough idea of what the services are that are operating. And these ones down here are the main ones that TopCat gives you access to. So cone search is the most straightforward. You just say to an external service, this is the sky position I'm interested in, this is the radius around it, and can you give me all the rows in your table which are in that region of the sky, that circular region of the sky. TAP, Table Access Protocol, much more complicated way of interrogating external catalog data, database data. And there you write a query in a language which resembles SQL, it's called ADQL. And you can write very complicated queries which burrow into databases and pull out exactly what you want. Simple image access and simple spectral access, they're a bit like cone search, except instead of just getting back catalog rows, they'll tell you about the image data that is in a certain sky position, or the spectral data that's in a certain sky position. There's a number of services run by CDS, that's the data center in Strasbourg, which are not, strictly speaking, VO services. They're not standardized, but they do very useful things. So for instance, Simbad, you can give it the name of an object, an astronomical object, and it'll tell you where it lives on the sky. Vizier is a database of many astronomical catalogs, pretty much all the ones you're going to need usually. They have a cross-match service and some other things, and we'll see some of those in the demo. The registry is how you do service discovery. So the registry is the big list of what services exist where. And usually the first thing you do when you ask TopCat to do some virtual observatory stuff is to say, well, I'm looking for a TAP service which has got Hubble Space Telescope data in it, for instance. And TopCat then goes to the registry and says, where are there TAP services which got HST data? And that tells it which computers to talk to get the data back. And SAMP, I mentioned very briefly before, that allows tools to talk to each other on the desktop. So it means TopCat can talk to Aladdin, can talk to DS9, can talk to Splat and various other things. I probably won't get around to demonstrating it this time, but it can be useful. I'll mention just briefly Stilts, which is a command line package which essentially does all the same things as TopCat. It's built on the same libraries. But you can use it in a scriptable way. So TopCat's it's good for interactive work, and especially if you don't really know what you want to do to a table, but you want to look at it and play around with it, TopCat's great. You point and click and see, and iteratively decide what operations you want to do on it. If you know exactly what you want to do with a table and you want to do the same thing on 100 tables one after another, then using an interactive interface like TopCat gets a bit boring. And so in that case, you can write a script using Stilts, which lets you reproducibly do the same thing to tables while you don't have to sit there with a mouse in your hand. There are a few pros and cons of the different things. For instance, Stilts in some cases can work with much larger tables than TopCat. But whether you use it or not depends really on the kind of work you're doing, and also whether you like that sort of thing. Some people are comfortable using command line programs and some people not. So you may never use Stilts, but it's there if you want to. Again, I won't say any more about that during this talk, but in the tutorial I'll point you to later, there's a kind of introduction to it, and the whole thing's documented online, which you should be able to find if you need to. Okay, so I haven't mentioned everything that TopCat can do by any means, and I won't cover everything that TopCat can do in the demo either. But everything is comprehensively documented. So there's a web page which has the user document linked off it. This is the URL for the web page, but you can probably just Google for it and find it if you look around a bit. And also on every TopCat window, there's this little help button. And if I click it, it will take me to the help browser internally in the application. and it'll take you to the right page of it. Or you can look at the same thing online in a web browser if you like. And there's also a search functionality in the help browser. So you can just start up the help browser and type in the topic that you're interested in, and hopefully it'll take you to the right section of the manual. If you want to print out the manual and read it from start to finish, don't let me stop you, but it's not really intended to be used like that. And finally, there's support available by email, so there's a mailing list which you're welcome to use. And I'm also always happy to answer questions by email if there's something that you don't understand what to do, or some feature that you'd like to see. So you can mail me if you have questions. Okay, so that's the end of the talking slides, and I'll do a demonstration after this. I'll stop there if anyone has any questions and answers now. I'm happy to answer them, or if not, I'll go into the demo.
Mark, yeah, good morning. Hi. Earlier in your talk, you mentioned that TopCat won't be able to do image processing. So how about one-dimensional signals? Like, for example, I get an electromagnetic wave data and in time series, and I want to plot the frequency. So does it have the FFT algorithm imbibed in it?
Yeah, okay, so it won't prevent you from using something that might be an image. If it looks like a table, if it's in the format of a table, TopCat will use it. So that covers time series and it covers spectra. So yes, you can use it for that kind of data as long as it's in a tabular format. If it's in a one-dimensional fits file, if one-dimensional fits image file, it won't pick it up. But if it's in a tabular format, it will. So it's already a complicated tool. One of the problems with it is that it kind of does too much already. And so I try to avoid adding lots and lots of new functionality to it just to avoid complications. So what it hasn't got is specific functionality to help it look at time series, to help it look at spectra. So I mean, you're welcome to try and use it for that kind of data. But if you say, I wish it did all this time series specific stuff, I may say no.
Yeah. Okay, so it won't be about the fast Fourier transform of the time series.
That's right. That's in the category of things I'm not planning to add.
Okay, all right, thanks.
Okay.
Are there any more questions from anyone? Or should we proceed? I think we can proceed.
Yeah, okay, let's go. I have this scribble on my screen here. Can you see this? I'm not sure how it got there. If you can work out how to get rid of it, feel free. But if not, maybe it's my problem.
We can see the screen demo 1, Pleiades and Gaia and Tumas.
Yeah, can you see these green scribbles on the blue?
No, we don't see any.
Oh, okay. Right.
Do you want to have the scribbles?
No.
Okay, because there are no scribbles over here.
Okay, well that's fine. I've done something with the annotation. I'll
actually,
just
we
ignore
switched
them.
off the annotations, so probably that's why it's not coming.
Okay, well that's fine. That's all right. Okay, so the first thing I'm doing is start up TopCat, and I'm going to first of all do something which is along the lines of what Priya did last week, but I'll go through it in a bit more detail and explain things as I'm going along, and I'll go a bit deeper into it as well. So I'm going to look at the Hyades Cluster and see what I can find out about that. So the first thing I'm going to do is go into the Virtual Observatory menu and click the clone search button. And I want to find data from the Gaia source catalog around a particular position in the sky. So this is what I was saying about the registry. I type in here Gaia DR2, find services, and then TopCat goes off and talks to the registry. Says, where have you got any cone search services which have got Gaia and DR2 written somewhere in their description? And there's actually quite a few here. I could refine it, but I'll pick this one, Ari Gaia. Oh, by the way, so the demonstration I'm going to give here, I don't know if you've got access to the slides that I'm giving, but I gave them to Priya, so they may be available on the website somewhere. So there's a summary. Well, I'll show you what it looks like. So there's a summary here of what I'm doing, and you can go back and work through it yourself if you like later on. And as well as that, towards the end, I'll point you at this tutorial here, which will allow you, and so that covers some of the same ground as this as well. So it's up to you whether you trying to follow along while I'm doing this, or whether you just watch me doing it. I suspect it's probably going to be easier for you to just watch me doing it, because the information that I'm telling you is available elsewhere, and you can go back and find it later if you want to. But if you want to try and follow along and you can do it at the right speed, then feel free. Okay, so this then is the machine, the service it's talking to get the information about GaiaDR2, and then I type in here Hyades, hit resolve. That goes off to Strasbourg to another VO service and finds out what sky position this corresponds to, and tells me that, and I'll get all the objects within 1 degree on the sky.
Sorry, Mark,
also,
but, sorry, 1 sec. But do you have a TopCat screen also open, or you're just showing the slides?
No, I have the TopCat screen. Can you not see that?
No, we can't see the TopCat screen. We can only see the slides.
Okay. Thank you for mentioning it. Let me see if I can. Is that any better?
No, no. We can still see only the slides.
Okay, that's
Now we can.
Now we can see it. Now we can see it.
Okay.
Good.
Right.
It's good. But we are sorry, but now we can't see the slides. I can see the TopCat thing. That's okay.
This part we won't have the slides.
Yeah. So now we can see TopCat.
Okay, good.
Okay.
So, all right. So yes, this is what I've done. So I typed in GaiaDR2. Here it found me services that talk to Gaia. I did this and hit the button, and it went off and retrieved a new table for me. So this is it. It's loaded into TopCat. And so having loaded a table, it's a good idea to look at it one way or another to make sure, or have an idea that you got what you think you've got to got. So here it says the 26,000 rows, sounds reasonable, and 46 columns. If I click these buttons along here, can you see my mouse pointer when I'm indicating things on the screen or not?
Yes, we can see your table. It's all fine. And your mouse too. We can see the mouse moving.
Okay, good, right. So these buttons along here give you different ways of looking at the table, basically. And this one here is the actual table data itself. So you can scroll up and down and see the numbers. They're all there. Looks healthy. But you can also see the metadata of the table as well. So if I click on this button, it takes me to the window which tells me all about the columns in the table. And as well as the column names here, which are kind of obvious, it tells you what data type, if it's a string or a double precision floating point, or it tells you the units, which is obviously essential to know if you're going to make quantitative use of these numbers. And if the person who's providing the table, the service who's providing the table, has put it in there, then it's got maybe a human readable description of these columns as well. So if FOTBP mean mag doesn't mean anything to you, then perhaps what's written over here tells you more like what's going on. There's also this UCD column, which kind of does the same thing as this, but in a way that the computer can understand. You don't really need to look at that, but it's there for machine readable purposes. So that's the table metadata. Another good idea when you get a table is to plot it on the sky to see if it looks reasonable. So these buttons along here are all different kinds of plots: histogram plot, plain 2D Cartesian plot, and a sky plot, and 3D plot, and so on. So I click this one, got a sky plot. So the plot windows are, as I said, kind of complicated, but to use them straightforwardly is hopefully not too difficult. So this is a plot on the sky. I'm going to navigate in and out by zooming. So the controls are like Google Maps, at least some of them are, and you can do other things as well. So I can zoom in and out using the mouse wheel or two buttons on my mouse pad. That's the whole sky. That's where the Pleiades live. And you can pan around with the mouse as well, obviously. There's various other options. So for instance, if I go to this axes control here, I can change the sky projection. So I can change from sine, which is the default, to an ITOF projection. That's an all sky projection, and that's where the Pleiades live, just in the northern equatorial hemisphere. If I want to see it in galactic coordinates instead, I can do that. So I change this to galactic, and you can see there it's in the below the galactic equator. And there's all sorts of other things you can do as well. You can change the number of grid lines and change the font size and all sorts of things, which, you know, first few times you're going to use it, you don't need to know, but there's lots of options there if you want to try to use them. Go back to where we were. Okay, so now I'll do a different kind of plot. In this case, a 2D plot. And here I'm going to plot proper motion in right ascension against proper motion in declination. So what this is telling you, okay, so the navigation here, I can zoom in and out again, but that's kind of the wrong shape. So I'll use a different navigation technique here. And to find out what the different mouse actions are, if you click on this tiny little question mark button at the bottom, it tells you, it goes to the help browser and tells you exactly what you can do, which different kinds of actions you can do with the mouse to move around the plot. In this case, I'm going to use the center mouse button, or if you haven't got one of those, a shift mouse button will do. And I can just draw out a rectangle on the plot, and it will zoom to that region. Another thing you can do is if you put your mouse just underneath one of the axes and zoom, it will zoom just in one direction like that. So there's various ways you can configure it to look at the part of the plot that you're interested in. In any case, in this plot, you can see there are obviously two very distinct subpopulations. These are the background objects here. Most of the objects in that region of the sky are not moving very fast across the sky. They're close to 0, 0. They're not quite at 0 because there's a bit of drift to do with where that position is in the galaxy and where we are in the galaxy and the rotation. But there's this subpopulation of objects here, which are all kind of zooming across the sky with a much higher velocity, all pointing in the same direction. So because it's a velocity plot, things which are close to each other on this plot are all moving in the same way across the sky. So we're going to identify these as a separate population. So I click on this blob button here. And when there's a tick on there, when that's highlighted, I can draw a little blob around here. And when I'm happy with that, I click on that button again, and it asks me what I want to call that subset of data. So I'll call it cluster. Click add subset. And then this set of blue points is now identified as a separate set of points than the red ones in the background. If I go to this tab here, the subsets, I can control these separately. So I can turn them on and off. I can turn the background objects off and just look at the cluster objects. Or I can change the representation of one of those sets of objects. So I can change those to pink if I want, and so on. And as you're doing different things, you may end up defining lots of different subsets. If you go to this window here, this shows you a list of all the subsets that you've currently defined so far, just these two, all and cluster, and it tells you how many in each one. So there's 540 objects in the cluster subset. Okay, so having done that, because of the linked views, let me see where we are. So if I go back to the sky plot, you can see, and again, I'll adjust some of the details of how this is plotted. So now you can see that these blue objects are the ones in this region which are co-moving across the sky, the ones we've marked as a cluster, and the background objects are not. Okay, so the next thing I can do once I've identified which these cluster candidates are is to look at the sorry, I'm having trouble with my mouse. Okay, I'll do a different kind of plot. I'll do a histogram here. So I click on the histogram button. That starts off with a histogram of something I'm not interested in. So I'll just change the quantity and I'm going to plot parallax. And again, I'll make sure I've got both subsets plotted. So parallax is, I won't explain what it is if you don't already know. It's something that the Gaia satellite measures, and it's a proxy for distance, basically. So objects with a high parallax are close to us, and objects with a low parallax are far away. And you can see, oh, you can't see too well. So the red objects, there's many more of them, are the background objects, and there's a small number of these cluster objects which are centered in a different place. To make it easier to see what's going on there, I'm going to change one of the options. So if I go into this bins, general, and change the normalization, I'll normalize on maximum. So what that means is, even though there are different numbers of objects in the blue and the red sets, it's normalized them so that they both have the same height in total, and that makes it easier to compare the characteristics of the two populations. So if I stretch them out, you can see that the background objects have parallax, which is near to 0, maybe about 1/2. But the parallax of these cluster objects is 7 and a bit by the look of it. And so that is telling you the mean parallax of the objects in the Pleiades, which in turn tells you how far away they are. To be a bit more quantitative about that, I'm going to do a slightly different. I'm going to change the plot a bit. So if I go here and I go to the form tab again, and in these forms I can do different kinds of plots which use the same data. And I'm going to add a Gaussian type plot here. Make that line a bit thicker. So all that does is calculate the mean and standard deviation of the objects in this distribution, in this blue distribution, and plot a Gaussian around it. And if I go down to the bottom of this tab here, I can actually read off the mean and standard deviation that it's calculated. So if I go to cluster, it tells me here that the mean of all these cluster objects is 7.2 milliards seconds. So I can invert that and find an estimate of the distance to the Pleiades. Slight word of warning, that works for the Pleiades. You need to be a little bit careful if you're inverting parallax in Gaia data to find distances, because the errors work in a non-linear way. So if it's a close object with small deviations, that's okay. But you won't always get a sensible result by doing that. There's papers you can read that will tell you the various pitfalls of that. So that's told us one astronomically useful bit of information about the Pleiades, how far away they are. We'll do something else now, which is look at a color magnitude diagram. So I'll do a different kind of plot again. Again, this is a sorry, I'm having mouse trouble again. Let's start that again. Okay, so if we look in the column data, amongst other things, there's this column BP_RP. So this is the difference between the magnitude in the blue sub range and the red sub range of the blue passband and the red passband of the photometry observed by Gaia. And this one here, FOT-G mean mag, is the broadband G photometry. So I can plot BP minus RP on the x-axis and FOT-G mean mag on the y-axis. Let's flip the axes upside down because astronomers like to do things backwards. And again, we can fix it so that the subsets are colored separately. And so what we've got now is a color magnitude diagram of all the objects that we were looking at. All the objects are kind of scattered around all over this color magnitude space because they're all at different distances and they're made of different primordial material and they're formed at different times. But if you look just at the cluster objects, they are mostly on this quite tight main sequence in the color magnitude diagram. And that's because they're formed at the same time. They're at a similar distance away, so the magnitudes resemble their intrinsic magnitudes. and they're formed from the same primordial material. They're in the same cluster. So you can see that's clearly something, you know, astronomically going on, and you can infer things about when they were formed and so on from looking at that and understanding the way that these color magnitude diagrams work. It's worth saying that not all of these are on this tight sequence. So these ones down here are probably interlopers. Probably we selected them from the proper motion diagram, and they were really background objects, but they just happened to be in the same region of proper motion space. So something else that we could do is to refine this cluster selection by doing another subset here and picking out just these objects. And we'll call this beta cluster. And then so this beta cluster object subset, which again you can see here, there's 418 objects in it. Those are more reliable cluster candidates, and you can refine the data in various ways by doing that sort of thing if you want to narrow down which are real cluster objects. So that's looking at the Gaia photometry. We might want to look at photometry of the same objects or information about the same objects from a different survey. So for instance, we can look at 2MASS data for the same thing. 2MASS is another large all-sky survey. It's in the infrared and it observed in 3 wavebands. So the table we've got at the moment is just from Gaia. What we want to do is match it with an external data set with 2MASS to find out if we can find data points, photometry points for the same objects in the infrared. Now, 2MASS is a large survey, so we can't download it locally. So one thing we can do is cross-match it using some kind of external service. There's various ways to do that. What I'm going to do now is use this button here, the Sky CDS Sky Crossmatch button. So this window will essentially allow me to take a table that's in TopCat, send it to a data center in Strasbourg, which has all the Visier data there. In Strasbourg, it will compare the objects that we've sent it with a catalog that we ask it to compare it to. It will join the 2 catalogs together and send me the result back. The first thing I need to do is say which external catalog I want to talk to. So 2MASS in this case. And it tells me about that. So there's 500 million objects in 2MASS, and it covers most of the sky. Then I say which of my data I want to send to it. Oh, actually, one thing I'll do before that, I'm not going to send it all the objects because I'm only interested in the cluster objects. So I'll set the current row subset, the row subset in the main TopCat window to cluster. I should maybe set it to beta cluster, but I'm not because I haven't tested that. So now when I send this data up to the cross-map service, it won't send all those rows. It will just send the ones that I'm interested in. So again, I tell it what are the sky position columns and how far away I'm prepared to accept 2MASS objects from each individual Gaia object that I send, and then hit the button. And it doesn't take long. It goes to Strasbourg, comes back as the joined table, and it's found 512 rows. So that compares to 540 rows in the original table. So it's found a match for almost all of those cluster objects in 2MASS within 1 arcsecond. So it's given me back a new table, which again I can see what it looks like here. And if I look at the columns in that table, there are more than there were before. So the columns from here to about here, first 46 columns are the columns that I sent it up in our original table, and these additional columns from 47 to 63, those are the ones which the service has joined on. And so each row in the table has now got the Gaia objects on the left and the 2MASS characteristics of the corresponding objects on the right. Okay, So having done that, I can do a different diagram. I can do a color diagram, because I've now got, as well as the Gaia photometry, I've got these quantities Jmag, Hmag, and Kmag, which are the photometry in J, H, and K infrared wavebands from 2MASS. So we'll do another plot here, and we're looking at the objects that came back. And so I can again plot BP minus RP from the Gaia photometry on the x-axis. There isn't a column that I can use to plot J minus K, the infrared color. But there are those two columns, Jmag and Kmag, and so I need to use the expression language this time. So I can't just select from the list of columns, but I can type Jmag minus Kmag, so that's using expression language, and there we go. So that's now a color diagram with the infrared color on the vertical axis, and the optical color, the Gaia optical color, on the horizontal axis. So again, we can see a kind of fairly tight sequence, but again, there's these outliers, and it'd be interesting to find out why they're there, what's wrong with them, why they're not really behaving like the other cluster members. So there's a few ways we can do that. The first thing I'm going to do is color these points corresponding to the parallax. So this button here, the shading mode, lets you do various different things. This is what I was saying before. The flat mode just colors everything the same color. The auto mode color things darker if there's lots piled up. But there's another option down here called weighted mode. And what that does is let you use another variable to change the color of these points. So what we're going to do is color them by parallax, and let me choose a different color map. Try that one. And I'll configure that color map. I'll tell you why I'm doing it in a minute. Make the points a bit bigger. Okay, so, oops, not that. Right, so what we've got now is a plot where these points have changed their color according to what parallax they're at. If you remember, the parallax of the cluster, the mean parallax of the cluster was about 7.2. So I've fiddled with this slider so that 7.2 is about at the neutral color there. So these kind of feeble gray points are objects which are more or less at the mean parallax of the cluster. And these ones which are dark brown or dark blue, those are the ones which are either, the brown ones are much further away than the rest of the cluster, and the blue ones are much closer than the rest of the cluster. So it's no surprise that this one's off the main sequence, because it's much closer. It's a foreground object, it's a background object. It's further away than the rest of the cluster. So this one shouldn't really be here. And same with this one, it's too nearby, and so on. These two as well, even though they're actually in the right region of the color diagram. But these objects here, they look like they should be okay. They're about the right parallax, but there's still obviously something wrong with them. So we can investigate those points in more detail to see what's going on. So if I click on any of these points, hang on, is this going to work? So if I click on one of the points in this diagram, I can see where it appears in this other diagram. So this was just the Gaia color magnitude diagram. But I can also, at the same time, if I get the actual table data up, I can see which row they correspond to. So this will show me the various magnitudes and so on. And I'm going to look at this column here, this QFL column. If I go to the column metadata, that will tell me that tells me about quality flags of the two-mass photometry. And AAA means basically they're confident of the photometry. But if I look at, let's see, this one, so this one is obviously there's something wrong with it. And if I look at the quality flags in the two-mass data, it says UUE. I'm not exactly sure what that means, but it's not AAA. So it means that there's something wrong or doubtful about the photometry. So it's not too surprising that this one is off the main sequence. If I look at that one, well, that one says AAA, so it's not clear what's wrong with that. We'd like to investigate him in more detail. And so what we'd actually like to do is have a look at the actual image that that two-mass took in order to identify this object in the first place and extract those magnitudes from it. So what I'm going to do now is go to this button. It's called the Activation Actions window. And what this does is let you configure TopCat to do various different things when I do this business of clicking on a particular point. There's many different options. But what I'm going to show you at the moment is this one, Display Hips Cutout. And what this does is it will take the sky position corresponding to a particular point, and it will go to an external service. Again, it's in Strasbourg. The data center in Strasbourg is it's got a lot of extremely useful stuff in it, and retrieve the actual image data corresponding to that object, so you can have a look at it and see what it looks like. Again, I need to say which set of image data I want. So normally I'd push this select button and I want sky data, infrared data. Now at the moment, since I wrote this part of the toolkit, there's got to be a lot more infrared data surveys than there used to be. And so this list now goes way off the screen. I fixed that in a more recent version. So for now, I can't select two-mass from this button unless I get a taller screen, but I can just type in the right value. And what I want is two-mass color. So that's the name for the survey that I'm interested in. And now, let me just fiddle around with it a little bit, get 500 pixels square, and let's have a 1.5 degree, no, 1.5 arc minute region. So now if I click on one of these objects, hopefully it should go off and request that image. So this image that you can see here is actually that object. This image here is actually that object. And if I click on this chap, that looks reasonable enough. If I click on this chap, you can see maybe why there's something wrong with this object. So this central object is the one that it's done the photometry for, but it's very near this other bright object. And so probably the photometry is confused, and this result has got spurious magnitude columns in. So that's why this results off the main sequence. So you can do this sort of thing. You can drill down and find out more information about subsets, successively refine data sets, look at individual points, see what's wrong with them, and get your cluster membership better and better. Okay, so that's the end of that part of the demonstration. I'll do another demonstration in a minute. But in the meantime, if there's any questions, we can, I'm happy to take them. So I can see a question in the chat, which is, can we scale marker points in the sky map proportional to its brightness from apparent magnitude? I think I've sort of answered that here. So you can scale the size of the points if you want. And what I'm doing here is scaling the color of the points corresponding to a different quantity. Does that answer that question, Himadri? And does anyone else have a question? Right, so there's another question here. TopCat's available on GPL. Suppose a user wants to integrate external plotting libraries like Matplotlib or vector manipulation libraries like Inkscape. Is it possible? Integrate, so let's see. I mean, it's a Java program and it doesn't talk particularly well with, well, it can talk to non-Java programs, but not at the kind of API level. So, I mean, you can export data sets from TopCat to Python if you want to use matplotlib. You can write out PDF files. You're talking about Inkscape. You can, in the next version, which will be very soon, you'll be able to export SVG image data as well. So you can construct a plot in TopCat and write out a scalable vector graphics file, which you could then import into Inkscape if you want to. But as far as talking to Python, you can use SAMP to communicate data between the two tools, or you can just export a data set, save it as a FITS file or save it as a VO table or something like that, and import it into other applications. I don't know if that answers the question. Okay, so another question. I have two tables that have common objects. Can I join them without getting the common objects twice? Probably the best thing, let's see. So there are various options in the cross-matching, in the internal cross-matching. They're in this joins option. If you've got two tables of common objects and they're marked somehow the same as each other, then you could probably do the match and then exclude objects which have the same identifier in the two, the same identifier from the two different halves of the join. So you could define a subset. I haven't explained how to do this yet, but you can define subsets algebraically as well as graphically. So you could call the subset something like non-duplicated, and then use an expression which would be something like identifier 1 is not equal to identifier 2. So you do the join and then exclude the objects which have got matched identifiers in some way like that. That would be one way to do it. Can we apply this to CSV or other files? Yes, you certainly can. So if I click this button here, there's just, or the file load, which is the same thing, load table. So from here, I can just load a table from local disk in the usual way. Well, these are FITS files, but if it was a CSV file, you could as well. Actually, there's one thing you need to know about CSV files, which is yeah. So let's find a CSV file. There's one here, I don't know what's in it. So if I just try and load this CSV file like that, it will say, can't do it. Try these different formats. And that's because it can't work out that a CSV file is a CSV file just by looking at it. For CSV files, or not for some other formats, I need to tell it that it's CSV. So I need to go down here to table format, right, CSV, and then OK. And then it will load it. And there's my CSV file. It's not a very interesting one by the look of it. Okay, so I'll move on to the second demo now, and I can certainly answer some more questions after that. Okay, there's another question. I'll just do that one first. Points with error bars. Okay, so yes, you can do points with error bars. I think this one has error data in it. Let's see. Yeah. Okay, so if I have a scatter plot like this, the zoom controls keep getting in the way of the other controls, and then I can't move the windows. Let's do that again. Okay, so here's a scatter plot, and I'll plot blue magnitude against red magnitude. And I also have these error quantities here, blue mag error and red mag error. So this is one thing that I tackle by one of the items in this forms menu here. So this gives you lots of different ways of plotting the data. There's various different ones here, but one of them is add XY error. So what this does is add another item down here, and these. So both of these are ways of plotting the data that I've got described here, and it gives me the additional options that I need down here. So in the XY error, X positive error, I can choose the B mag error, and for the Y positive error, I can choose R mag error. And then you can see there's error bars there. I can choose different values for the positive and negative if I want, and there's various other options. So you can change how those things are plotted. You can have them as error ellipses if you want, and or rectangles or whatever it is you want. So yeah, there's ways of plotting error bars. Restrict the possible data points to a limited range of error. Yes, so again, you do that by using one of these subsets. So if you only want the objects with a relatively small error, I can say, let's see, what are those error bars? So I define good and 5. Let's just make that even smaller, so I can change that by just editing in there. That's 0.2. Replot that, and then you can see that the blue objects are the ones with small errors, and the big objects are the ones with the red objects are the ones with big errors. And I can unplot those, and then just have the ones with the small error. Okay, right. There might be more questions later, but I'll go on to doing.
Sorry, Mark, sorry to interrupt, but we have a YouTube feed also. So I have questions on YouTube.
Oh, sure.
I'll
Yeah.
read it out. So there's a question by Priyanka. How can we remove the stars which do not lie in the 3 sigma of the fitted Gaussian from the selected cluster?
Yeah, okay. So there's a couple of ways of doing that. Again, one of them is to, let's see if you have original table. So again, given that the, do I still have my parallax plot? One of the problems of using TopCat is you get an awful lot of windows and it's very easy to get lost. I'll just go back and do it again. No. Right, okay, so here we are again with the Gaussian. It's not all right. I want to plot parallax. So there we are. This is the characteristics, mean 7.2 and standard deviation 0.6. So I can define a subset again algebraically like this. Push this plus button. So I can call that 3 sigma. And then I write in the expression using the expression language just parallax is greater than 7.2 minus 3 times 0.68, and use 2 ampersands. Parallax is less than 7.2 plus 3 times 0.68. So that's one way of doing it, and you can see they're just there and there. A more straightforward way, maybe, you can do it graphically by just identifying the bit that you're interested in. So if you reckon that's 3 sigma, you can do it by eye, or you could work it out. You can use this button here, which defines a subset based on what you can actually see in the window at the time. So it just picks out this bound and this bound, and essentially does what I'd done up there for the 3 sigma one. So I can call this middle, and it'll add a subset, which is just those objects which I can see. So that's a couple of different ways of doing that. There's a question on the chat: can we access data from VOs using stilts? The answer is yes. There are stilts commands to do cone search queries. There are stilts commands to do tap queries. I'll talk about tap in a minute. There's a stilts command to do the CDS upload cross match. There are not stilts commands to talk to the registry. So sometimes what you need to do is to use TopCat to work out what service you want to talk to, and then you can use that information and plug it into a stilts command. Okay, I'll go on to the second part of the demo.
Sorry, Mark. One more question.
Mm-hmm.
Can we compute the turn-off point of a cluster analyzing data in TopCat?
Okay, so now we're reaching the limits of my astronomical knowledge. I'm not an astronomer by training. Probably the answer is no. If you can see what that looks like on a plot, and you can, so if you've got something like a color magnitude plot, and you can see this is the turn-off. I have no idea if that's what turn-off looks like. You can look down here in this position panel near the bottom of the window and read off what that number is. So that might tell you what you want to know. But you can't say to TopCat, please tell me what the turn-off point is. You can look at the data yourself and try to assess that.
Yeah. So add to that, since I work on star clusters, you'd need your isochrones and stuff like that and to show it and justify it.
So you can load isochrones into TopCat as as a set of data points, and you can plot them. But you're on your own trying to understand what that actually means.
That's right. Yeah. So I think we are done with questions, and we can.
Okay.
Yeah.
Right. Okay, so the second thing I'm going to do is kind of similar to the first, but this time we're going to tackle a more difficult problem. We're going to look at the Hyades cluster. Now, the Hyades is much closer to us than the Pleiades, and one consequence of that is that it's spread out over the whole sky, not over the whole sky, but over a large portion of the sky. So with the Pleiades, where we could say we just want 1 degree worth of data, with the Hyades we can't do that. I'm not sure how big it is, but it's I think tens of degrees you need to cover the whole thing, and that's really too big search to make to a cone search query. So we need a more complicated way of phrasing that question. And in order to do that, what we're going to do is use TAP. TAP is the table access protocol, and as I say, it's much more complicated but much more powerful than cone search. Priya, I don't know, have you covered TAP at all yet or not in the course?
No, I haven't.
Okay, sure.
I just did basic cone.
That's fine. So this window here, we'll open up a TAP window, and this is quite a complicated window. It does lots of different things, but in some ways it's the same as the cone search, which it allows you to select an external data service and talk to it in a standard way. So in this case, what we want to do is find the Gaia TAP service. Oops, it's just listed there. You can again search for it by name, but since this is all the TAP services in the world, so that you don't really need to do a search, you can just choose it from the list. That takes you here. So this then tells you all about what that TAP service has got, what data it's got. Here, so if I click on this service tab, it tells me what it is. This is the name of the service. That's where it lives. It's run by the European Space Agency. This is who you complain to if it doesn't work properly. And then down here is listed in a hierarchical way all the table that it's got. What we're interested in today is Gaia DR2. It's got other Gaia data releases in there as well. And if I click on one of these, it tells me about that table, what it is, how many columns it's got, a description of the table. And the one that we're interested in is Gaia source, Gaia DR2.Gaia source. That's the main Gaia source catalog. That's the main table that's in this database, really, although you might want to use some other ones as well. And so it says it's got 96 columns, says what it is. It's got 1.7 billion rows. And if you go here, this shows me the column. So this looks like the TopCat column metadata window, but it's not the same thing because you haven't loaded this table yet. It tells you what columns there are in the service. So these are, again, actually the same things that we saw before, but these are the ones you can ask for. There's more than we had before because the cone search doesn't give you all of them. So I'm not going to give you a TAP tutorial here, at least not an ADQL tutorial. So ADQL is the language that you use to request data from a TAP service. It stands for Astronomical Data Query Language. If you happen to know SQL, which I guess stands for Standard Query Languages, I don't know. But SQL is an industry standard language for talking databases, and it's essentially a dialect of that. So I'll just give you a very simple example, and then I'll show you the kind of complicated example. So a very simple example does something like select, let's see, select top 10 RA deck source ID from Gaia dr2.Gaia source. So what I've written there is give me the top 10 rows, because I don't want all of them, there's too many. These columns, RA deck and source ID, they're all listed up here somewhere, RA deck and source ID somewhere. From, this is the name of the table, Gaia dr2.Gaia source. If I click run query, it will go off, ask that service, which is in Madrid, and get me back this table. And there we are. It's got what I asked for, the RA deck and source ID for just 10 random rows. If you want to investigate TAP more, in more detail, you certainly can. So this hints tab here is a reasonable place to start. It gives you just a few simple templates for how to write TAP queries, how to write ADQL queries. And there's a few links down here. One of these is the Gavo ADQL introduction. So that's a course run by the German Virtual Observatory, which will take you through ADQL from the start. So if you want to investigate that, by all means do. Another option is to look at this examples button down here. If I click basic, it will give me just some very basic queries, which you can run and kind of look and adapt to your own purposes. And if I look in the service provided ones, these are a bunch of queries provided by this particular Gaia service, which are much more complicated, or at least they can be, but these will run and you can examine these and see how they work and maybe do similar things yourself. But the one I'm going to use today is, let's have a new tab. So I'm going to pinch it from the slides. Someone's got their hands raised. If they can ask me a question, feel free. Okay, maybe later. Okay, so this is the query I'm going to run. I won't say in detail what it is, but essentially I'm asking for the RA and deck, the sky position, the proper motions in 2 dimensions, and the parallax and the radial velocity. So that's the motion in all in 6 dimensions, so the position in 3 dimensions and the motion in 3 dimensions. So it's enough information for me to work out how all the objects are moving in 3 dimensions. And I'm asking for objects, parallax greater than 15, that means one's nearer to us. Parallax over area is greater than 5, ones where the parallax is reliable and where they've got this radial velocity. So I'm asking for all the nearby objects where we've got the 6-dimensional phase space information. And I'm hoping the Hyades objects will be in there because they're nearby and they're close enough that Gaia has been able to observe how fast they're moving towards us or away from us, as well as how fast they're moving across the sky. So there we are. We've got that result, 26,000 rows, and it's got the columns I asked for. Now, although that's got information about how these are moving in 3 dimensions, it's in spherical polar coordinates. And what I want to do is transform that to 3D Cartesian coordinates so I can see what the motion looks like in 3D. In order to do that, I need to use one of the functions in the expressing language. If I go to this button here, this FX button, this is the documentation of the functions available in the expression language. So it's got various things. These are just the arithmetic expressions. So this is just a documentation window, trigonometric expressions. If I click on these, it tells me how to use them. One of the options is these Gaia functions, and there's various things here, but the one I'm going to use is this one, Astronomy UVW. So this does what I was talking about just now. It converts the motion and position information from Gaia, RA deck parallax, proper motions and radial velocity, into Cartesian coordinates. And I'm just going to cut and paste this and add a new column based on it. So to add a new column, I click in the columns window, and like in the subsets window, I can click on this plus button, and that lets me add a new column with an expression that I give it. So I'm going to call it UVW, and the expression is just that one that I lifted from the documentation of that Astronomy UVW function. I don't have to, but I'm going to type in the units, which I happen to know are in kilometers a second. Okay, so now I've got a new column here. If I look in the table data, there's a new column here, and you can see it's not a single number, it's a three-dimensional array. So this is velocity in the x direction, velocity in the y direction, and velocity in the z direction. And now I'm going to plot those in 3D. So this time I use this button here, the 3D plot. So there isn't a column for each of these x, y, and z coordinates. I have to use, again, another thing with the expression language, which is to dereference array values. So the first element of the UVW array, I can call UVW0. If you're used to programming languages like C, this will look familiar, but if not, it's not too complicated to work out. UVW0 and UVW2. So that's the x, y, and z velocity information. So what we're seeing here is, change the shading again. Okay, so what we're now looking at here is all those 26,000 objects which are nearby us in velocity space. So this is a three-dimensional analog of what we had in the proper motion plot. And the objects that are close to each other in this plot are ones which are moving in the same way in 3 dimensions through the galaxy. So the navigation on the 3D is a bit more complicated than the 2D for kind of obvious reasons. It takes some getting used to. Again, if you click on this little question mark button, it will give you some hints. But the two useful things to know are you can rotate around it like this, as you'd expect. You can zoom in and out around the center using the mouse wheel. But the non-obvious thing is if I right click, or let's see, it's a control click if you haven't got a right mouse button. If I right click on a particular position, it will recenter the whole plot on the thing that I've clicked on. So if you can see that little overdensity there, there's a little dark blob there, which is lots of points stacked up on top of each other. If I right click on that, it recenters on that, and I can zoom in. And so these objects in this overdensity, it's the most obvious feature in velocity space near us, is the Hyades. These are all moving through the galaxy with the same motion. They're far apart from us on the sky. They're far apart from each other on the sky, but they're all moving together and they're part of the same cluster. So having done that, having fixed the view so that I can only see those objects inside my cube, I can push this cube button and define a subset based on those. So I'll call those cluster. And if I go back and change the colors again, you can see those are in blue and the non-Hyades objects are in red. And if I go back to the sky plot, do I still have a sky plot? I'll get a new one. But let's have an all sky plot. So that, again, the red objects, the background objects, let's turn those off. So these are the objects that I've identified in the Hyades. Now, some of these are probably interlopers, but this is where the Hyades are on the sky. So you found that out. And then you can go along and do the same sort of thing. You can plot color magnitude diagrams. You can find out the mean direction, the mean distance to them, and so on. Okay, so that's all I'm going to say as far as demonstration goes. The rest of this will be free form. I guess, are we nearly at the end of the session? I think we are. However, I'm happy to stay here for at least another half hour or as long as people have questions, if people still have questions. Apart from that, if you go back to the slides, I don't know if you have access to them.
I'm sorry, I didn't share it with the students.
Oh, that's okay. Well, here they are. I'll put it in the chat, in fact. Well, I'll do that in a minute. Oh dear. So this here is a URL to a tutorial. It's also linked from the TopCat webpage, and that goes through some of the things that I was showing just now, plus some more advanced stuff, plus some more, plus an introduction to starting introduction to stilts as well. And so if you want to do some things on your own, which are not just kind of reproducing what I've done or starting reproducing what I've done and doing some other things, then you can work through that tutorial either now or at some later date. Let me see if I can put it in the chat.
Yeah, I'll share it on the website, so it's okay. Don't worry.
Okay, it's in the chat.
Yeah. Okay.
Right, so thank you for your attention, everyone. Am I right? Is that at the end of the time session by now, Priya?
Yeah, in principle, yes.
Okay, so it took me longer than I meant to go through that. I meant to leave some time in the session for people to do free-form explanation and answer some more questions. But as I say, I'm happy to stay here and answer questions for as long as anyone's interested in. I can see in the chat someone asked about what operating systems you can run it. So it runs in Java, which means it will run on pretty much anything. It will run on Windows or Mac or Linux. You just need to make sure that you have Java installed. Java 8 for the current version, although for some reason you can't get Java 8, it'll run in Java 6 for some earlier versions of it. And that is usually fairly straightforward to set up. There's not too many system dependent issues. If you've got a Mac, there's a DMG file as well that you can get, which just makes it slightly more straightforward. Mac people like that sometimes.
Yeah. Yeah, so the floor is open for questions, please. I had a question. To use that UVW format, I've never used that before. That was something new for me too. Does it have to be, does it only work with Gaia data, or, I mean, how does it use the metadata?
Oh, but those functions are, let me go back to here. So these ones in the Gaia section are convenient for use with Gaia. So for instance, these ones, they use the same units that you get from Gaia data. But if you can get that information from some other place, then yes, you can certainly use it for other data sets as well. But just make sure that you've got the quantities in the right units to use in that case.
Okay, so that conversion would have to be done by you itself, and then you feed it into this.
That's right. So that's it, yes, you'd have to do it yourself. But I mean, you can just do it by writing in the expression where you where you calculate it. So for instance, if you've got parallax in arc seconds rather than milli-arc seconds, then you just write parallax times 1,000 in the expression there. So you can do the conversions within the expression itself.
Okay, yeah, thanks. What about the others? Gitanjali asks, do I have to run my DMG every time I want to launch TopCat? What's a DMG?
I was distracted before because when that came up first, it said I have to run my dog every time I wanted to launch TopCat, which sounds fantastic. I was trying to work out why. That sounds like a question about Macintoshes, which I don't really understand. I think there's a DMG file which you can, if you install it, you can click on it or something and then it runs. But someone who understands Macs might be able to answer that more straightforwardly than I can.
I don't use it. Okay, you have a comment on...
Someone asked if you can use TopCat for anything other than astronomy. Yes, for sure. I mean, it works with tables, and so anything that's got a table, you can shove into it and get as far as you want to. I mean, the funding has always been astronomy so far, and so that's what I've spent effort doing. And the other thing is, in practice, developing a tool like this, it takes a long time to persuade people to use it. You know, even if it does the job well. And so I haven't attempted to go out into other communities and push it to, you know, for instance, geophysicists or mathematicians or whatever it is. But various people in other sorts of areas, there's some people use it in life sciences, some people use it in finance even. I think someone uses it in flight testing. So yeah, there's no reason why you shouldn't use it for other applications. But the kind of specialized features in it are mostly for astronomy.
There's another question from the YouTube feed.
Mm-hmm.
Can we automate the selection of possible cluster members from a number of clusters based on density instead of selecting the area manually?
That's a good question. Okay, so there would be, is there a way of doing that? Okay, so the answer is certainly not that straightforwardly. One thing you can do is, let me see. So this is a somewhat larger table. There's a couple of million rows in here. And let's see. That's not a particularly sensible plot, but you can make grid maps like this. So you can modify. You can make binned maps over a certain area of whatever your parameter space is. And having done that, you can you export that? Oh no, you can't export that, so that wouldn't help. So no, not very easily, I think is the answer to that. If you're sufficiently ingenious, there are some stilts commands you could use to do it. You could generate a density map and export it to a FITS file and then analyze that FITS file to do it. But it's not a straightforward thing to do in TopCat, no.
Yeah, there's another question, which I think you can read.
Yes, okay. So maximum execution time, 30 seconds, reached, job aborted. Okay, right. That's a good question. I'm glad you asked it. So this is one of the many, many things that can go wrong when you do a tap query. this particular service, the Gaia service, will only let you run a 30-second job before it says, no, that's too long, I'm not going to let you run it like that, you've got to do something else. Some other services will give you longer timeouts, so you might see that, or different errors elsewhere. However, there's an easy solution for this service. So if you look down here, just above where the ADQL query is, it says mode synchronous or asynchronous. Quick look, ignore that. So by default, synchronous means it sends the query and then waits on the same HTTP connection for the result to come back. And it's designed for relatively quick, straightforward queries. Asynchronous does something much more complicated. It schedules a job to run at the remote service. The remote service runs it, and then the client can keep polling it. The details don't really matter, but asynchronous is intended for running longer jobs. So the answer to your question is try running it in an asynchronous mode, and hopefully that should work in that case. Now you can still get timeouts if it takes a very long time in asynchronous mode, or maybe it just takes ages and ages. So as is often the case with the virtual observatory, you do sometimes have to play around. Another option, if you can't get it to work at all, is to look for the Gaia data on another server, because Gaia in particular lives in various different places. So, if you don't have any luck with the ESAC service, then have a go on other services. But the answer to that particular problem would be use asynchronous on the tap query. So there's another query, another question about the tutorial. Matching HST and Gaia data. Okay, let me see if I can find the actual picture for that. So this is in the tutorial where you're doing a different kind of cross match, and you're matching data from HST observations with, I think, Gaia observations. Oh, there isn't a picture of it. But it turns out that when you do the match, you get objects where the HST data corresponds to 3 or 4 different objects in the Gaia survey, or maybe it's the other way around, I forget. And the reason that happens is just because your search rate, is because your search radius is too wide. So there's no guarantee that you'll get one object corresponding to one object when you match 2 surveys with each other. It depends on the errors in those surveys, whether there's some sort of systematic offset, all sorts of things. TopCat will just say this one is close and this one isn't. In that particular case, I think there's a systematic offset. So the HST data is actually not pointed at exactly the place on the sky that it thinks it is. When I first saw that data, what I actually thought was the difference of the stars, that the stars actually moved significantly between when the HST data was taken and when the Gaia data was taken, because they are stars with a non-zero proper motion, and there's 10 years or something between the surveys. So it could be both of those things, but I think in practice it's mostly to do with the fact that the absolute astrometry on the HST data is not exactly correct. But that is an example of the sort of thing that TopCat isn't going to tell you. You need to you need to kind of think about the data, think about the astronomy that's going on underneath it, and try and work out what's going on, and then you can tell TopCat how to do something to do something about it. There's another one on the chat. Can I indicate missing upper or lower limits when plotting error bars? Well, yes. So, I mean, that's just a question really about how you represent the error bars. Do I still have my error bar plot? But I don't. I get confused about how to use this stuff. No. Okay, so there's some error bars, and they're the same in both directions. If I want to do error bar, so I can have different error bars for I'm trying to think what an error bar would look like to represent a missing one. If it was just if you just wanted to show that there was no error there, if this value is a blank value, then I think the error bar won't show up on that side.
But can you put your condition there itself? For example, Big Mac error less than something. Would it work?
Yeah, you can. So, for instance, you could write BMAG if it's greater than 0.2, don't show it. So this is one of the conditional expressions I was talking about. Is that going to work? So I know that's not quite what you're asking about, but what this says is if the error is greater than 2, then plot it as if it was a 0 error. And if it's less than 0.2, then plot it as normal. If you want to show different sorts of error representations, what you can do is have 2 different sets of error bars plotted on top of each other. So you can stack as many of these things as you want. And for instance, this one you could represent using arrows. And then maybe you could have BMAG error is greater than 0.2 query. So then the large errors you could represent using these little arrows, and the little errors you could represent using without arrows. And you could do something similar with null values as well if there's a blank value there. So if you want to have only represent them. No, it doesn't work.
But similarly, can you use your quality flag, which is a string, to mark the counter points in the sense of weighting them or something with a string?
Yeah, so you can write some sort of expression which uses strings. So you could say if the string is equal to some value, then do one thing, and the string is equal to another value, do something else. Yeah, using a similar sort of syntax. Yeah. By the way, since we're over time, by all means, everyone can leave if they've had enough, including Priya.
No. I'm done. Okay, there's one more question, which I can see. Probably you can also see it. Avik Dasgupta. That's it. Oh, there's one. I've worked through the tutorial you shared. One of them is about cross-matching HST and Gaia.
Okay, yes, that's what I was talking about when I was saying about the...
okay, sorry.
I did that one.
Yeah.
Does JSAMP talk to TopCat? Yes, in fact, JSAMP is inside TopCat. So yes, TopCat does talk to other tools using SAMP if you wanted to. I haven't demonstrated that, but yes, it can talk to Aladdin, for instance.
Yeah, we have also not yet done that in our sessions, but we'll be doing that. Yeah. So, are there any more questions? Or so I guess everybody can try working out the tutorial and right.
Okay, so if people could put their hand up on the thing, or I don't know if they've got other options, if they would like me to stay on because you might be doing the tutorial, but if everyone's gonna go off and do something else, that's fine. I'll slope off.
Yeah, I think we can stop now. because everybody can, they need to digest what they heard. And then,
It's fine.
in case there are many queries, we can get back again, if it's fine with you.
Yeah, it's important now for them to try that out and come back with issues, and then we'd come to you if we can handle it ourselves. Thanks a lot, Mark, for being with us.
Okay, thank you very much for your attention, everyone.
Thank you so much. It's really very nice. Thank you so much. Big thanks from everyone. Thank you. Bye-bye.
Bye-bye.
I end it.